Hi, welcome to the CKAD MasterClass lecture series for learning Kubernetes. By preparing for a certified Kubernetes application developer exam by Cloud Native Container Foundation. I am Aniket Kanade and I will be with you along this journey. So let's begin. So this is our agenda for this lecture. We're going to go through the history of computing, starting with the bare metal servers to the today's world of cloud native computing and where Kubernetes stands in the landscape of cloud native computing. So this is a prerequisite lecture, and if you have a good idea of what virtualized servers are and what containers are and what Kubernetes is, you can skip this part. In early days of computing, everything was bare metal computing. What would happen in a bare metal computing would be there is a physical server located in the server room with racks and CPUs and disks that are easily you can go and see them, you can identify them, and you know where the server is located, how it's running, how it's connected with its electrical circuitry. It's a physical server, and that would run several applications which would communicate with the external world via TCP/IP ports. So this was the software aspect of the server, where application and ports were software elements and they are not visible to the eye, but they just exist in a software layer. Now a computer would communicate with the web server running on port 80 using HTTP protocol, and the web server would internally go and fetch in the file system of the server an index.html file and return it back to the computer requesting the index.html file. That's how a simple bare metal computing client server communication would work. And all other complex workloads and communications were built on top of this simple form of communication where the request comes in on a given TCP/IP port and responded to by the server listening on that port. So what were some of the drawbacks or disadvantages of bare metal computing? First and foremost, a company running any kind of application has to own the physical infrastructure. So they need to own the servers, they need to manage the servers, they need to manage the networking of the servers, they need to manage the upgrades of the servers, keeping the infrastructure, operating systems, all the applications up to date. That was quite a huge task, and so that was not easy for a very small scale firm to own computer applications. Second drawback was on demand scale. Well, it's not possible to scale a physical infrastructure just because there is sudden rise in the demand, and scale needs to be planned. For example, if it's online marketplace and they see increasing orders, they need to provision more hardware to service them in advance than waiting for actually the orders to pick up and then go and do the scaling of the hardware because they want to process more orders now. So on-demand scale is not possible with physical infrastructure. The cost of running physical infrastructure, the networking aspects. So if you have several different geographically located sites and you are having servers located at different parts of the world, networking them together on a private network, that itself would be quite a task. So that and all these were drawbacks of bare metal computing, which led to the era of virtual computing. Virtual machines. The advent of virtualization of physical servers to create virtual machines, or as we normally call it, VMs, was the landmark step in the cloud native evolution. In case of VMs, what you have is a host with a large pool of processor and memory allocated to it. The host is capable of creating several virtual machines on demand. From the end user point of view, the existence of host is transparent. The end user still sends the request to the IP and port of the VM, and the VM would respond with the requested data to the end user. As we can see in this example, a browser running on the PC requests for index.html on the VM, and VM responds with the file from the file system. Nothing changes from an application developer point of view as well. The application runs exactly the same way as it would on a physical server. With the emergence of virtual machines, it became possible to host a small application in a rented server of a cloud provider. It was no longer necessary to own physical hardware or maintain it in order to run software applications. It was also easier to scale the resources by adding more processor and memory in the host, or create and destroy capacity on demand. Yet there were few challenges too. For example, it was not easy to have VMs talk to each other when they are hosted on different hosts. Also, resource allocation in case of VMs is quite tight. A VM that has excess capacity present in it cannot provide or give up its capacity for the other VM that is resource starved. In summary though, virtualization came with several benefits and advantages and was the first most important step towards the progression of cloud native. Containers. Coming to containers. The story of containers is quite interesting. What we have here is a large host which is a bare metal. It contains several VMs inside of it, and each of the VM runs several small containers which are application containers. Although containers can be hosted on bare metal directly, that is usually not the case. The end user interaction still remains the same. The end user sends HTTP request to an application listening on a port inside container, and the application responds directly to the requester. VMs provided hardware virtualization, whereas containers enabled application level evolution towards cloud native. Containers provided application encapsulation, dependency management, application portability, and ease of deployment. Idea of containers and microservice architecture go hand in hand. An application comprising of several containers, each hosting a single microservice, is quite typical of a modern application. So that's it about containers. Next we will see a quick demo of a simple Docker container, and then we will see what is container orchestration and Kubernetes. Hi, so here we are going to do a sample demo of containers, and with the help of a Docker container we are going to see how container works in virtualized environment. So let's begin. This is my VM, Linux based virtual machine, an Ubuntu virtual machine that I use for my development purposes. and it already has Docker installed. So, and we are going to use an image called BusyBox, which is a lightweight distribution for learning purposes. And let's have a look at. I don't have it right now on my system. I think so. Yeah, so it's not there, and we can run a Docker container. Before we begin, just a note that I have marked this terminal as red because we are going to use this to run the container and enter the container shell, and this terminal, that terminal tab that is highlighted in green, we will use it for the host commands. So let's begin. The command to docker run -it -rm busybox, this command will download busybox from Docker Hub and will also start a shell in that image, in that container. So as you can see, it's the image is pulled from the Docker Hub and it is started. Now we are in the shell of a container. This is not the host shell, and we can verify it by looking at ls. And if you look at ls home, you can see there is nothing in there. And if I do who am I, it says root. So this is altogether a completely different VM. It looks like a different machine altogether, but it is actually a container running inside a virtual machine. As we can see from the host, this is home of host, this is the root file system in host, and so this, and if you look at yes wrap, we can see that there is one process running in host, docker run busybox, which we executed, and everything else is running inside this container. This way the container provides isolation of processes. But one main difference between a container and virtual machine is virtual machine creates a resource pool, a set of processors and memory that is allocated to the virtual machine, and the separation between the host on which virtual machine runs and the virtual machine itself is pretty hard. Once you are inside virtual machine, you cannot access anything on the host, whereas the separation between a container and its host is not that hard. It is possible to run the things on host. It is possible to share the resources between host and the container, and also the resource allocation is fluid, and container itself doesn't have its own processor or memory allocated, but it takes from the host. So, and this is possible because of Linux namespaces. What happens when we run a container under the hood is Docker creates a Linux namespace for that container, and all the processes for that container actually run on the host, but they run inside a Linux namespace. For example, if we run a shell command in this container, as you can see, the 30-second sleep is running on the inside the container. And if you look at the command from the host, the command is actually running on the host as root. So even though the command is running inside the container, it's actually started on the host, and it's running as root. And this is possible because if we take a look at the namespaces, the namespace PIDs, and this is the command that displays the PIDs. And if we look at the namespace that's running busybox, what we can see here is this is the namespace created by Docker, and everything is running on that particular container is running inside this namespace. The sleep command has exited, that's why it's not there in that namespace right now. But if we run it again, Yeah, you can see this is the sleep command that we started inside the container, but it's actually running on host inside a namespace. And this is how the separation is achieved by Docker by creating Linux PID or Linux process namespaces. So that's it quickly about Docker, and we'll head to the next sections. Before getting into container orchestration, we must understand what container orchestration is and what is the need for it. Imagine a real-world scenario of a medium-sized app. The application will be hosted on at least 15 to 20 VMs with at least 20 to 30 microservices requiring at least 100 replicas. Some services require more replicas than others. Some services require geographic spread, whereas some services require continuous availability. Some execute themselves in a batch mode, while some are cron jobs. Can you imagine what nightmare it would be for sysadmins to manage this kind of a system? Running hundreds of containers across tens of VMs while ensuring all the conditions met requires a specialized administration and monitoring application. That application, which is like a platform on which cluster is configured, is called Container Orchestration Engine. Kubernetes is the most widely used container orchestration engine. When Kubernetes cluster is formed, we assign a pool of VMs to the cluster and ask Kubernetes to use those VMs for container orchestration. Now let's look at some of the things Kubernetes is responsible for. Provisioning a cluster of configured VMs and monitoring the VMs. Scheduling containers on the VMs, maintaining container state, monitor replicas, manage inbound and outbound traffic, ensure continuous availability and redundancy as per the configurations, manage upgrades, fault management, etc. So that's it for this lecture. This lecture was a prerequisite for CKAD's Kubernetes certification. And in this lecture, we went through the history of computing, how it all began with bare metal computing, and where we are at in terms of cloud native computing, Kubernetes, etc. today. If you have any comments and questions, do let me know in the comment section, and see you in next lecture. Bye bye.